Sure.
Nice to see all of you, friends. Hello, those of you on camera and those of you who are blacked out. I can see your names there, so hi. Thank you all for doing our second fall lunchtime talk. For friends, I'm sorry we're not actually having lunch together in the dining hall at IAS. But I very much appreciate that Richard Schwartz has agreed to speak with us today. Rich is Chancellor's Professor of Mathematics at Brown University, a current member in the School of Mathematics. He's here at the Institute for a second time, actually. He first visited in 2003-04. Rich did his undergraduate work at UCLA and went on to earn his PhD at Princeton University in 1991. He held positions at University of California, San Diego, Mathematical Sciences Research Institute, the University of Chicago, and the University of Maryland before his appointment to the faculty at Brown. Rich is the recipient of numerous honors and awards, including Sloan, NSF, and Guggenheim fellowships. And in 2002, he was an invited speaker at the National Congress of Mathematicians. At IAS, his membership is funded by a grant from the Ambrose Monell Foundation and a Simon Sabbatical Fellowship. In addition to his research as a mathematician, Rich is the author of many comic and children's books, including Really Big Numbers, which was featured in his first family science talk that he actually gave at the Institute in 2015. And some of you may have seen Rich's recent family science talk a couple of Saturdays ago. If you didn't, it would be fun for you. And if you have children or grandchildren, it was recorded and you can find it on our website. I highly recommend it. While here at the Institute, Rich is working on simple questions in geometry, topology, and dynamics, particularly as investigated through computer experimentation. We're very pleased that he has joined us today. We are all intrigued and look forward to hearing about tantalizing mathematical problems. If you would go ahead and mute your audio, we'll have time for questions and discussions after the talk. Rich, it's all yours. Thank you.
I'm going to share the screen. So I like, I don't always work on these kind of simple problems, but sometimes I really like geometry, and I like computer programming, and I also like these kind of simple problems, and I'm hoping that at least a few of them will kind of pique your interest. And they're things you can play with yourself. I mean, it's really fun. I think of, well, somehow some of these famous unsolved problems, they're like these giant mansions, kind of unapproachable, but the guards will kind of let you into the lobby. I mean, you can have a look around and play around a little bit. This is my feeling. I'm often kind of playing around in the lobby of these things. So I'm going to talk about four things, four kind of problems that are or were out there, and the first two are really pretty famous, and these little emoticons have kind of indicated my success level with these problems. The first one, I just didn't get anywhere, no progress at all. The second one, I'd say I got kind of a nice result, but I didn't prove the thing. The third and fourth ones, I mean, I don't want to put all these problems in the same category. I mean, they're not as important as the first two, but one of them I actually solved, and then one of them I may have solved, but it's something I've been working on here at the Institute this year. And maybe one moral of the story is that human knowledge is very extensive, but it's also very spotty. It's sort of amazing both what we know and also what we don't know. And I feel it's a little bit like what happens is someone will make some progress in some area and it will prove to be fruitful, and then more people will enter into that direction, and they'll create these kind of long corridors of knowledge, almost like trails through the woods. But then sort of most of the woods are just completely unexplored. I mean, it's kind of surprising that there are these very simple things that you can pose, but nobody knows. And I think what's really interesting about these simple unsolved problems is that they're kind of pregnant with possibility. You think, well, in order for them to be solved, you need a completely new idea, like sort of a new notion, like a new zero or something. And so I think this is what attracts mathematicians to them. It's this idea of like understanding some fundamental new thing that will make progress on these problems. So I'm going to go through and I'm going to describe these four things. And I'm also going to show some computer programs I wrote which help investigate the problem. So the first one is the Graceful Tree conjecture. And this was, posed around in sometime, I don't know, I said 1967, but it's around that time. And one of the people, Kotzig, he said that working on this problem is sort of like a disease. So anyway, so here's what it is. So a tree it's just a bunch of, it's like a network. It's a bunch of nodes that are connected by edges. And the thing that makes it a tree is that there's no loops in it. So these trails that you could follow around, they don't kind of cycle back around and close up. That's what a tree is. And the game is that you label all the nodes with numbers. The first however many numbers you need. In this case, 0, 1, 2, and 3, and then in the one on the bottom, 0 up to 8. And after you label the nodes, the pink nodes, you label the edges according to the difference of the nodes. So this edge here gets a 2 because 2 minus 0 is 2. And in this picture, this edge here gets a 4 because 6 minus 2 is 4. And the labeling, like, I want to look at this top row. There's a kind of tripod here in black and one in yellow. And the difference between them is that in the one in yellow, there's repeated edge labels. Here you see a 1, a 1, and a 2. And here you see a 1, 2, and a 3. And the labeling of the nodes is called graceful if you don't see any repeaters. So here, or another way to say it is you see all the numbers. So here you see labels 1, 2, 3, and here you don't see 3 and you see 1 twice. So this yellow one is ungraceful and the black one is graceful. And here I'm showing a more complicated example, which also is graceful. If you look at the differences of the nodes, you see all the labels. So it's a little bit like a game of Sudoku. And the graceful tree conjecture is that any tree, no matter what you draw, will always have a labeling like this, a graceful labeling. So just very quickly, I didn't do much with this problem, but I want to just at least show you a program I wrote that gets you started in investigating it. So this is a problem. This is a program that I created in Java, and what you can do is you can kind of create your own tree. And you can, if you prefer, you can move it around, and so there's a nice tree, and then you can just push the button, and it will kind of, in a sense, it will search through all the possibilities. And so on this control panel, I'm going to push the button, and there it found a graceful labeling for this tree. You can in case the numbers are too small to see, there's a 1 and 5 and so on like that. So that's what this program does. And at least for small trees, it will succeed. Like I can add some more to this tree and push the button again, and it works again. So at least for kind of small ones, it always seems to find it. There are some preset ones, like here's a nice one that's preset, and it sort of searched like 25,000 possibilities and it found one. So, but you can have really, really complicated ones like so, and then if you push the button, it's probably going to fail. So anyway, this program isn't so powerful, but at least it's a start in kind of approaching this question. Okay, so that's the graceful tree conjecture, and some kind of small attempt on my part to explore it experimentally. So the next on the list is the square peg conjecture. So this one is a really notorious one. So what in the upper part of the picture, what I've drawn here is a continuous loop. It's just, you could think of it as like the shoreline for a lake, if you like. And what I've drawn here in red is there's 4 points on it, which are the corners of a square. The square is in red. And the conjecture is that no matter what continuous loop you draw, there's always 4 points on it that make the corners of a square. And there's been a lot of work done on this for the past century, but so far kind of no cigar. Like people don't know how to solve in general. And to illustrate this, I've drawn an extremely complicated, well, I haven't drawn it, I lifted this off the internet, but okay, maybe I picked a bad example, but you can have continuous loops which go around and do this. I think maybe I don't quite, as I trace around this thing, I think maybe it's not quite connected up. But you can imagine a sort of what people would call a fractal loop, where when you start zooming in on it in small scales, it gets more complicated, and then you zoom in some more and it gets more complicated, and so on. And can you always fit a square in one of these things? And at the moment, people know it if the loop is, if it's not a fractal, you could say it like that they know the answer. But for sort of these really complicated ones, they still don't know. So I was going to show you a program I wrote which explores this. So here, here's an example of the white curve is the curve, and then this is showing you the squares that are in it, and it can change from 1 to 3 if I move this around. I can also complicate the curve, and you'll see these squares kind of come and go, and one thing you notice about the program is that there seem to be a lot of them. Okay, it's getting to be a big mess. You can also simplify it again. But one thing you may notice, if this 5 here in the corner, it counts the squares. And if you keep track of this number, you see it's always an odd number. And as you move this around very gently, you could probably see that there's two squares coming together and then they're disappearing. And in fact, when the loop is a polygon, it's true that there's always an odd number of these squares, and the proof is more or less that nothing much happens until they kind of either are born in pairs or die in pairs. And so you sort of start with an odd number for some curve you understand really well, like a triangle, and then you start moving it around. And so the square peg is this problem is known for polygons, but not for these. If you start complicating the curve more and more, you always get a square, but maybe like if you try to, take some limit and get some infinitely complicated loop, then all the squares disappear in the end. Well, I got interested not just in the squares, but also in the rectangles. Here I'm sliding a lever and I'm changing the aspect ratio of the rectangle. So this is sort of showing you all the rectangles, that not just the squares. I sort of thought, well, you notice that the rectangles, as you change their shape, they kind of move around. In a sense, they kind of sweep through the whole curve. And I'll even show you an animation of this. Here's a single kind of family of rectangles that just sort of sweeps through the whole curve. And one thing I discovered is that basically this always happens. So at least notice that as this thing sweeps around, the corners of it actually trace out the entire curve. So every point on the curve, except maybe 4, where it kind of collapses, is the corner of a rectangle that fits on the curve. So I'm going to say something that this kind of experimentation did inspire a result of mine. So I'm going to kill the program. I'm going to show you. I wanted to at least. So here's my result, that even that no matter what kind of crazy loop you have, with the exception of at most 4 points, you can find a rectangle that is inscribed, which means that the points are on the curve, and one of the points is your point. So wherever you put your finger, with maybe 4 exceptions, there's always a rectangle you can draw that involves that point. So this is sort of an example where, of course, I was interested in like the square peg conjecture, the main thing, but I didn't solve it. But then I solved some other thing. That's pretty common in mathematics research. It's kind of lucky. If you're an engineer and they wanted you to build a bridge and you built an elevator instead, you'd be fired. But if you're a mathematician, it's okay if you try to solve one problem and you end up solving another. So anyway, that's the square peg conjecture and something about it that I did. The next one I'm going to talk about is called outer billiards, and this was kind of, you could think of it as a little bit like you're playing golf, but you're not very good at golf. So you hit the ball and you're trying to hit many of us have had this experience. It almost goes in the hole, but it just kind of glances by the hole and keeps going. And then you try again. But you want to say this in a very precise way. You have this red region, which is the hole, or the playing field, if you like, or the table. And then what you do is you move this one here is supposed to be a single point. You move it along so it just glances off the shape. You call it drawing a tangent. and it goes out as far as it was. So if this was 1 foot, then this would be 1 foot out. And then it just kind of continues on its path. It goes to here, maybe this is a foot and a half, and then to here, and so on like this. And then it would just keep going. This would go forever, unless it could, there's some rare instances where the process is not defined, but basically if you just pick a kind of a random point, it will go forever. And then some people thought of this as a kind of a toy model for planetary motion. You have a kind of a red sun and then a kind of a little point planet that's moving around it. And it's not obeying the usual laws of planetary motion, Kepler's laws, but it's obeying some other kind of laws, which are simpler, but it turns out share some of the features. There's a kind of an equal areas rule in Kepler's laws, and this equal length thing is related to that. But anyway, one of the main questions in this is, can the point wander away? Can you construct a shape and a point so that as you go around, it moves further and further away, maybe coming back, but in other words, can it kind of drift off arbitrarily far away from the shape? And this is a little bit like the question about the stability of the solar system. You want to know, like, if the Earth is going around the sun, is it stable? Is the Earth eventually going to wander off? Of course, the Earth wouldn't have to wander off very far before we're all killed. This is a more theoretical thing. It's asking, can it wander it's posing kind of an infinite planar universe, and can the particle wander off like as far away as you like? And I'm going to show you some pictures of what this thing does for particular shapes, and then this is one I actually did solve. So here's my shape. Maybe I can make it. Okay, it's blue rather than red, but you click on a button, and I guess I made it going around clockwise counterclockwise rather than clockwise, but this is what happens if I click a point. It moves to there, and then it moves to there, and then it moves to there, and this is showing all the places it goes before it. Well, I'm plotting like 100 points. If I plot more points, it's sort of moving all over the place. So sometimes when you click on a point, it makes a very predictable pattern, and then somehow if the orbit of the Earth around the sun looked like this, we'd boil to death. It wouldn't be good. But it is bounded. It's not going far away. And there's a kind of a nice example. And then somehow, as you sometimes see very, very beautiful things, and out there it looks like the thing is just generally going around, and close up that's kind of a neat one there.
Richard.
Yeah.
I'm so sorry. Could you make that a little larger?
Sure.
Great. Thanks.
Actually, maybe I can't make it too much larger. I think the program wants.
That's better.
So that's a kind of an interesting picture. If you start somewhere and you start playing this game around this shape, this is what you see after about 1,000 steps. And then if you click in the middle, it looks nice, and I'm kind of changing the start, and different things are happening as I click in different starts. So this particular example, if you want to know what the shape is, it's sort of a half of a circle joined with half of an ellipse. Anyway, for this shape, nothing is known. I mean, you can make these numerical plots, but nobody knows what happens. So I'm going to show you, if you if instead your shape is a polygon, you sort of see other kinds of features. So I'm going to show you another program I wrote, which is much more extensive, that kind of studies this for polygons. So this is my shape. And just to warn you, the picture is going to look different. I'm not going to plot individual points. I'm going to plot whole kind of packets of points because it's easier to see what's going on. Like what this red square here, when I do the system, every point in this red square goes to this red square. And then every point in this red square goes to here, and then over to here, and then over to here, and then back. So rather than kind of plot individual points, I can sort of plot all of the things at once. To maybe, it's almost like everything happening in this region is kind of happening in lockstep. And then I can pick a different start. And this is what happens when I click there. There's this little triangle. It's the biggest region. These regions I'm drawing are the biggest regions where everything is just doing the same thing in that region. You could think of it as like voting blocks. It's like all the people that are going to vote the same way on all the issues. Although maybe this is not a good time to talk about voting blocks. But anyway, you can kind of fill this picture in and just see what everything does. So now I'm getting lazy and I'm not changing the colors each time, just so I can do this more quickly. And then something pretty cool happens. There's a copy of the original shape that sort of goes around, and then further out, I'll try to find it. Now I'm just jumping around trying to find where it is. There's another copy of the shape, and it just kind of keeps going. So I'll try to clean this picture up a little bit so I can show you what's happening. So there's kind of, this might be a color blindness test for some people, but there's sort of these blue necklaces that go around, and in between it, there's this kind of complicated stuff that's happening. And all of this shape here, there's kind of a number that describes how far out the point is. And if I pick a different shape, it's a little hard to see, but well, I can change the shape and see what happens when I change it. Like maybe I'll do 3/7. And now the picture kind of looks different. Things are kind of going out further. And there's still a kind of a magic point where you get this kind of necklace. So you still get these kind of rings that go out, and in between them, kind of crazy stuff going on. And if you pick a really complicated fraction, which for me could be like 5/17, that's complicated enough, then when you click, it makes a pretty big mess. It goes out kind of a long way. And if maybe I'll pick an even bigger one, say 17 over 53. And then when I click somewhere, it kind of goes way out. So I sort of discovered that as you change the parameter, you get these kind of bigger and bigger things. And this suggested to me that maybe you could really get these unbounded, these kind of orbits that wander all the way away. So so I'll just say what I did. My result is that if you start with a shape like this, where it's a quadrilateral four-sided figure, and it's got bilateral symmetry and the ratio of areas is A, whenever A is irrational, then the answer is yes. You can start and move around and go as far out as you like. So anyway, this was an example of a problem I really solved. Okay, I have one more of these, which is the thing I've been working on at the Institute, partly this year. So a Moebius band is, what you do is you take a strip of paper and you give it a twist, and then you tape it together. That's what a Moebius band is. But you could ask yourself, well, can I make do with less? Like, could I take a shorter strip like this, and can I give it a twist and make a Moebius band? And well, this still works. But then, like, suppose I do it again, cut off some more. Can I still do it? Well, now it's getting a little bit complicated. And so the question is, how short can you make the piece of paper and still do it? And here I've shown what people think that the answer is. If the width of the paper is 1, say 1 inch, then the best you can do is square root 3. So this picture is supposed to indicate a folding pattern for the best answer. So I'm going to do this with a piece of paper. You take your piece of paper and you kind of draw these lines on it, as I have, and then you fold it in like this. So it makes a kind of a checkerboard pattern. And then you fold it like this and you tape the middle seam together. So the middle picture is what I'm showing here. And then the last picture is this thing is just folding up like a wallet. And then the seams are taped together. So anyway, since the 70s, people thought this is the best answer. And maybe I'll just quickly show you. I tried to also study this with a program. So what my program will let you do is you can sort of you can sort of move the thing on the right here is like a plan for one of these folded up things. And the thing on the left is what it looks like when it's all folded up. So you can sort of move things around. You can click on these creases and change the amount that they're folding, and sort of so I tried to write a program that lets you kind of model this thing quickly. And maybe I'll just say my results. I got somewhere. I didn't quite prove that square root 3 is the best, but what I proved is that you need almost square root 3. You can possibly do a little better, but you can't quite do the whole thing. And so this is the first thing I did. And the second thing is that I feel like I sort of have solved this problem because what I can say is that the conjecture is true if certain complicated expressions are never negative. So what I've been doing for the last month or so is working on these kind of complicated expressions and trying to show that they're really always, never negative, always positive, and that would solve this conjecture. So just to summarize, that was what I was hoping to do, just explain these 4 things that I thought about. Some of them are kind of famous, and sort of my mixed success on these various problems. So that's it.
Thank you, Richard. You would be willing to take some questions?
Absolutely, yeah.
Oh, okay.
There's the first question about, okay, Serge, does the conjecture say that the graceful labeling is unique? That's a great question. So let me answer it like this. Unfortunately, no, because if it was really unique, like if there was some, like if it was unique, you might say like there's some magic formula. You just kind of, you do some trick and you can just presto, there's the answer. So it would sort of, these kinds of problems where you're trying to show something exists, there's kind of 3 regimes in my mind. Like one is it's unique, or there's very few solutions, and those are more tractable often because you kind of know what to aim for. Then there's conjectures where like there's millions of things that will work, like almost if you pick an example at random, it works. And those people sometimes solve almost by using probabilistic methods, which is kind of what I just said. Like, yeah, you just show that if you pick something at random, it works. The problem with the graceful tree conjecture is that there's sort of a lot of solutions, but not that many. It's sort of like in a population of 1 billion people, there'd be like 87 solutions or something. So it's sort of like there are too many to think that there would be a formula, and then there's too few for there to think that there'd just be some random method that would work. So it's sort of like in a regime that's very hard for human beings, I'd say. Yeah. I can't. Oh, you were muted.
Am I muted now?
I didn't hear what you said.
Yeah, no, of course not. Can you talk a little bit about how so this is your second time at the Institute, how your work has evolved over that time, and what sort of this year, I mean, this is a very unusual time, obviously, but
right.
The pandemic aside.
Yeah, so I'd say, actually, I mean, so last time I was here, I'd say I kind of was kind of working on sort of one thing. I had sort of a big project I'd been working on. I mean, it eventually became a book, like a research monograph. And so, I sort of would say that like last time I was here, I considered many fewer problems. I mean, I kind of, I still feel like I'm mostly ignorant of mathematics, but like when I was here last time, I was extremely ignorant of mathematics, and now I'm just very ignorant. Like somehow I feel like I'm always surprised by how many new things there are out there. So now I'm kind of more, I'd say more eclectic, and more, and I'm actually also kind of trying to think about harder problems in a way. Like, I do feel like I want to just kind of swing for the hills in a way. Yeah, so more, just throwing more Hail Mary passes, and I got, last time I was here, I mean, the Institute was, it was great. I kind of finished a lot of things at the Institute last time, and this time I mean, it's more kind of random. A guy last time gave a talk about using, some things have changed. Like someone gave a talk yesterday about using artificial intelligence in certain areas of math, the deep learning. And I've got some problem I'm interested in, which I thought could apply it. So, I feel like I'm more reaching for different areas now. It is a weird time at the Institute. I mean, it's not the same as what it was. I mean, it's still really cool, but it's different. Like, not being, we all know, right?
How would you label your field of mathematics?
Probably broadly geometry and dynamical systems. Mostly, there's other things I've worked on, like geometric group theory and Lie groups, and even some differential equations. Sort of but I think mainly I'm a geometer. That's my favorite of all mathematics. Like I like shapes the best.
So if I could just ask one more question.
Sure.
You certainly use computers to lead your
Yeah, that's right.
Are any of these proofs, would you label them as computer proofs, or?
Some are. So in one of the, so like I didn't talk about one problem I solved was called the Thomson 5 electron problem, where you want to know, like, if you put 5 points on the 5 kind of charged electrons on the sphere, what's the configuration that they make to minimize their total energy? And I did solve this problem, but I solved it with a computer assisted proof. And it was this, essentially it was like a kind of a try all possibilities in an intelligent way, and see that the one that you think is the best, which is this thing called the triangular bipyramid, is the best. So yeah, I've done that a few times. I mean, it's and then this thing about this outer billiards thing with the thing wandering away. This was kind of mildly computer assisted, but I had to do some calculations, which I guess in a couple of years I could have done them by hand or something. So that often, the downside of doing computer experiments is that often you discover things that are true, but then you just don't have any idea how to prove them, because you don't arrive at them through any kind of precedent, or if you're you're just stuck with some fact, like, where do I go from here? And sometimes there may not even be a good proof. It might just be like, yeah, I just tried all the possibilities and it worked. So I've done some of that, and I'm never happy when I do that. Like, it's sort of, it's wrong. In my opinion, it's wrong in all kinds of ways, but like it doesn't seem to be durable. Like, I mean, computer programs degenerate every 10 years. So if part of your proof is like, yeah, I wrote this in Java 8.0 and you push the button and it works, in 20 years, it won't work for anybody. And then, so it's not, logic seems to be more enduring or something. So I guess I just say I'm not happy with it, but I'm not above doing it. Yeah.
Richard, you're unusual or unique in that you are a research mathematician who has taken the time to write children's books.
Yeah, that's right.
I'm wondering about your thoughts on the state of K through 12 math education, and more specifically, whether you think kids should be exposed to more of the unsolved problems to give them a sense of what mathematics actually is.
Yeah, that's an interesting, I mean, I think, yeah, that's a question I could spend a long time on. I mean, in general, I've been pretty, how to put it, like generally, I'm pretty unhappy with K through 12 math education, with some exceptions. Like, I know some wonderful teachers, so what I'm saying is, like, every once in a while I'll meet a teacher who's just fantastic, who, I mean, the thing about being exposed to unsolved problems, that I'd say more broadly, what I think is missing in education is that people being exposed to uncertainty, this idea that your teacher may not know the answer. And in fact, nobody may know the answer. So there's lots of questions people ask in all kinds of subjects. I mean, just the philosophy, I don't know, economics, and all kinds of things. And you get this idea when you're young, like there has to be an answer. It's got to be known. It's in the book. And it would be much better, I think, if people were just, if they taught people to just say like, we don't know, that's an acceptable answer. You know, we're trying to figure it out. But so, yeah, it would be great if people, I mean, you know, it's for math education, it's a little tricky because there's, you know, it is a very tall subject. There's lots of things you have to know. I mean, even, you know what I mean? Like people need a lot of skills in mathematics. They need to know how to do the basic operations and, you know, long division and things like that. So, you know, solving algebraic equations, it's a little, you know, it's a question just of like allocation of resources. Like they only get an hour a week or something. So I'd say like, it might be nice if like 15 minutes a week, they said, let's talk about some interesting thing that people still don't know, you know? So yeah. And again, like in all subjects, like, you know, I think like, we don't know, my brother's a neurologist and he tells me like, you know, they don't know why people sleep. Like, why do you really sleep or something? Why do you need it? Why do things go bad if you don't? So, you know, these are kind of like really central, you know, basic questions that nobody really knows. And it would be nice if from a young age, people were aware of that. It would, you know, make people more, I think it would make people more curious and more feeling like they too could contribute to knowledge. Like if you think everything's known, you're kind of discouraged. Like, oh, I just have to slog through 20 years of stuff that, in fact, you can just start investigating things. And you know, so anyway, I'm not conveying the depth of my disappointment of some things in K-12 education, but I don't want to go on a rant about things that they do wrong.
Hey, Richard, I've got a question.
Sure.
In your outer billiards problem, you initially described it as you take a point, hits the tangent of your shape and goes out a set distance before turning around and coming back and looking for the next intercept.
Yep.
If you're only going out a set distance, how does the pattern keep diverging and get larger and larger?
Well, oh, that's a good question. Well, you go out the distance that, you know, if you were like 1 foot away, you go past it 1 foot away. So the idea is that maybe you go out 1 foot away, but then you notice that you're further from the shape. Like now you're 2 feet away.
Okay.
And so then you go out 2 feet and
Oh, so you go out the distance that it took you to intercept.
exactly. Yeah,
okay, that's it. I got it now. Okay.
That's right. But it's very slow. These things that I found, they actually, not only do they go out, they keep returning. Like they sort of go out and back in a kind of erratic way.
Okay.
They eventually get as far as you like, but they also amazingly get as close as you like. So they take these kind of slow steps.
Huh. Be kind of interesting to constrain it to just a fixed distance and see what
That's
happens.
right. Yeah, that's a good point. People have tried variants. Like one variant is like you only like go out like 90% of as far as you were, like, so you're kind of generally moving inward.
Yeah.
And stuff. And you know, each one of these things kind of, I'd say it's kind of its own game.
Okay.
In a way. There are lots of fun. I mean, yeah, I mean, it's, you can try all kinds of things, and even if you like to program.
I'll stop coding now.
Right, if you like to, you know, I mean, somehow, it's again what I said. Sometimes, you know, it's a little bit funny. Like, actually, this is a good. Maybe I'll seg to this question: what makes a problem interesting, and one not interesting, even though both involve similar concepts? That's a really great question. So why is the Riemann hypothesis interesting? Well, and as opposed to the Goldbach conjecture. I mean, they're both interesting, but maybe what grabs people about the Riemann hypothesis is that, yeah, they're talking about the distribution of primes, but then suddenly you've got this kind of function which is sort of a function of a complex number. And so like, so let me say something amazing first. So like one thing, the best thing I ever learned in high school is that the sine function and the exponential function are really two halves of the same equation. Like they seem completely different. One of them kind of goes up like this and the other one goes like this. And you don't even learn them in the same classes in school, but there's a function of a complex variable. When you sort of look at it on one axis, you get the exponential, and when you look at it on the other axis, you get the sine function. And the thing that goes into the Riemann hypothesis is exactly that kind of function. It's like a function where it's sort of defined in the plane, and it has this really complicated profile, and you want to know, like essentially, when does it kind of dip down when you go along kind of the imaginary axis or some offset of the imaginary axis. And so it looks like it just has nothing to do with primes. It's like really remote, and then boom, it does. And so it's sort of like, you know, it makes you feel like knowledge is kind of connected at sort of a high level. Like, whereas the Goldbach conjecture, you know, maybe just you want to know sort of facts about primes, like is a number, or the twin prime conjecture or something. Like, it's just that there hasn't been the same, these complex functions. I mean, there were sort of, they come up in electricity. I mean, Riemann was also interested in electricity and, you know, the flow of electricity, and it's like the same thing. And so you wonder, like, what does electricity have to do with primes? It comes up in, yeah, like, I mean, Maxwell's equations are similar to these kinds of functions in the Riemann hypothesis. So it's sort of like you're seeing like all of math is somehow related, and physics is related to primes. And so it's a very, the Riemann hypothesis is very rich some way. The kinds of problems I was talking about actually I think are interesting for a different reason. Like, I mean, the Riemann hypothesis is interesting for many reasons, but in particular for its depth and range of subjects. And some of these unsolved problems, they're interesting because I think that they're kind of pregnant with potential. Like, all the ideas that people know about currently don't work. So they're sort of pointing out holes in our knowledge. Like in other words, in order to solve them, you would need some new insight. And it's surprising that there's even simple things. Every year, new simple things come out that just, you know, people, I mean, you think that only very complicated things would be discovered, but actually it's not true. Like there's kind of just new ways of looking at things that sort of evolve every year. And so sometimes an unsolved problem is interesting because it seems to point the way towards some other, you know, or suggest that there's some hole that we can fill, something like that. So the thing I wanted to say is that sometimes, I mean, I actually, I don't feel that strongly about working on things that are important all the time. I actually just, mostly I'd like to enjoy myself. I mean, I like mathematics, and, you know, I get to do it. And, you know, it's a bonus if, you know, I think most mathematicians would probably admit that finally, that if, you know, that they like to work on stuff because they're personally curious about it. And then if it turns out to be really useful in some way or important, then it's a bonus. But you sort of never know. Maybe that's the point. You never really know in advance. Like, just start working on something and see what turns up, I guess. Yeah.
Can I ask if you have an opinion about why math does turn out so often to be so tremendously useful? I mean,
yeah, lots of people have thought about that. I mean, so math, you know, I think here's what I think. I mean, I think that in a sense there's simple rules that math arises from kind of simple logical rules, and there's some initial, I mean, math isn't anything in particular. It's just systematic thinking about certain kinds of things, numbers and shapes and data, anything. And so I think in physics, it's the same kind of thing. Like, you have maybe interacting particles, and there's certain rules for the way they interact, or, you know, chemistry and it's sort of, so I think like it's all these subjects are sort of like, they're all following the same basic paradigm, just simple things interacting through rules and gaining complexity, you know, through that. And so math just kind of grows up in parallel along these things. And so all you have to do is, in math, you just have to tune your, you know, what you're studying to the problem at hand. Like, you say, well, okay, we have these particles, and what are the rules? How do they behave? And then if you you just follow it out mathematically, you're just sort of mimicking what's happening. So it's almost like it's just a good imitator of all the other subjects. Yeah, that's what I think. I mean, it is, it is kind of amazing that things work. I mean, they work astonishingly well. Like you just see these incredible patterns. And, there's a related question, like, is math discovered or created? And, it's, to me, it feels like it's mostly discovered. Like you just because you see these things that nobody would ever have guessed. But it is a really good question on me about the usefulness of math. I don't know if that answers it or not, but that's a fascinating question.
Thank you.
I think we have time for one more question, if anybody has a final. No? Okay.
Great.
Well, Richard, thank you so much. And thanks to all of you. Our next Friends Talk at lunchtime will take place on December 11th. And at that time, friends of the Institute member in the School of Social Science this year, Lori Balfour, who is a professor at the University of Virginia and a current Guggenheim Fellow, will be giving a talk. She hasn't given us her title yet, but her career has focused on exploring the political, cultural, and moral legacies of slavery and insisting on their ongoing importance to understanding democratic life. So that should be very interesting. Whole other spectrum from what you did today, Richard. But thank you very, very much. We wish you all the best in this funny year at the Institute. We're glad you're here. Thanks to all of you. Have a good weekend.
Okay.